myself, B2, with the Academy of Science and Technology. Our topic is one-dimensional wave equation. The wave equation is an important second-order linear partial differential equation for the description of waves as they occur in engineering and physics, such as sound waves, light waves, and water waves. It arises in the fields like acoustics, electromagnetics, and fluid mechanics. Historically, the problem of vibrating string, such as that of a musical instrument, was studied by D'Alembert, Euler, Bernoulli, and Lagrange. In 1746, a French scientist, D'Alembert, discovered the one-dimensional wave equation, and within 10 years, Euler discovered the three-dimensional wave equation. One-dimensional wave equation is dou square y by dou t square is equal to c square dou square y by dou x square. Really, the situation is you take a flexible string like this and you fix both ends like this. Then you pull it aside. Then you can see it vibrates like this. And we can prove equation of motion of this string is dou square y by dou t square is equal to c square dou square y by dou x square, which is our one-dimensional wave equation. Derivation of one-dimensional wave equation. You take an elastic string, let it be tightly stretched and fixed at 2 points. Let it be fixed at 2 points, O and E. Large tension so that the effect of gravitation and other external forces are negligible. Choose OA as the x-axis. And OY as the y-axis. Let the string be pulled aside and released. You can see it vibrates about OA as its equilibrium position. Next, we have to derive the equation of motion of the string. For that, we have to make a few assumptions. Assumptions are: the string is made of homogeneous material, that is, mass per unit length of the string is a constant. There is no effect of gravitational and external forces. The only force acting on the string is tension. The vibration takes place in a plane and small. Finally, there is no horizontal displacement. The string be pulled aside and released. Then you can see it oscillates like this about OA as its equilibrium position. Next, we will prove the equation of motion of the string is dou square y by dou t square is equal to c square dou square y by dou x square. And it is known as the one-dimensional wave equation. For that, you consider any point on the string. Since the string is moving up and down, the vertical displacement at any point on the string depends on two factors. You consider a point on the string, then its vertical displacement y. See, this is its vertical displacement, let it be y. Its vertical displacement y depends on two factors. One is the distance from the origin O, distance from the origin, and also it depends on the time. You take another point here, its vertical displacement is again depends on the distance from the origin and the time. So the vertical displacement y depends on two factors: the distance from the origin, say x, and the time t. That is, y depends on x and t. That is, we can consider y as a function of x and t. To derive the equation of motion of the string, you consider a very small element pq of the string. You consider a small element pq of the string. Assume q is very close to p. Let p be the point xy, p be the point xy, and q be x plus delta x, y plus delta y, since q is very close to p. And the tangents makes angles. You draw a tangent here, and here also you make a tangent. Assume the tangent at P makes an angle theta with the x-axis, and tangent at Q make an angle theta plus delta theta with the x-axis. See, the vertical component of tension at Q is T sine theta plus delta theta. Again, the vertical component of tension at P is T sine theta. See, our assumption is the only force acting on the string is its tension, and there is no horizontal displacement. The only displacement is vertical. So, the total force on PQ is T sine theta plus delta theta minus T sine theta. That is T into sine theta plus delta theta minus sine theta. See, our assumption is displacement is very small, so theta is very small. So since theta is small, we can consider sine theta as tan theta. So this is T tan theta plus delta theta minus tan theta. Again, tan theta is the slope at P, and tan theta plus delta theta is the slope at Q, and slope is its first derivative. So T into dou by dou x at Q minus dou y by dou x at P. See, Q means at x plus delta x, and P means at x. See, this is the total force acting along PQ. Again, by Newton's second law of motion, we have F equal to ma. See, the total force acting along PQ is T dou by dou y of dou x by dou y of x plus delta x minus dou x by dou y of x. See, this is the total force acting along PQ. That is T into dou x by dou y at Q minus dou x by dou y at P. See, by Newton's second law of motion, this is ma, where a is its acceleration. Suppose m is the mass per unit length of the string. Then mass of the element PQ is m into delta x. M into delta x into, see, this is the mass of the element PQ, and acceleration is dou square y by dou t square, which implies dou square y by dou t square is equal to t by m dou x by dou y at Q minus dou x by dou y at P divided by delta x. As Q tends to P, we have delta x tends to 0. So taking the limit, delta x tends to 0. Then the right side is T by m. When delta x tends to 0, this is dou square x by dou y square. That is the definition of differentiation. That is dou square y by dou t square is equal to t by m dou square x by dou y square. See, t is the tension, m is the mass per unit length of the string. So both are positive constants. So this is a positive constant. Let it be c square. So we have dou square y by dou t square is equal to c square dou square y by dou x square. See, this is the equation of motion of the point P. So we can generalize, this is the equation of motion of the string and it is known as the one-dimensional wave equation. So the one-dimensional wave equation is dou square y by dou t square is equal to c square into dou square y by dou x square.